Hey everyone, and welcome back. You know, one thing we spend so much time on as data scientists is feature engineering. It's super important. It can totally change how well our models perform. But let's be real, sometimes it feels like guessing. You're trying out different ideas, hoping something clicks and boosts your score. But what if we could get some smart help with that? Imagine if an AI could actually brainstorm new feature ideas for us, maybe even write the code. That'd be pretty amazing, wouldn't it? Well, today, that's exactly what we're going to explore. We're going to see how we can use a powerful language model, Google's Gemini Flash, to help automate feature engineering, specifically for a problem involving geographic shapes. You'll want to stick around for this, because the results are pretty darn cool. Alright, so here's the setup. We're tackling a Zindi challenge focused on agriculture in Côte d'Ivoire. The main task? Figuring out the crop type, like rubber, palm, or cocoa, just by looking at the shape of the field it's grown in. Our data comes as these GeoJSON files, which basically define the boundaries of the fields using polygons. This notebook is based on Mohammed's benchmark, which achieves score of 0.52. Let's see if Gemini can improve the score. So, naturally, we start with our usual imports. We need GeoPandas since we're dealing with shapes on a map, pandas for handling our data tables, and other helpful tools. We load up the training data and the test data using GeoPandas. Looks like we have about 950 examples to train on, mostly rubber and palm crops, and then about 280 test examples where we need to predict the crop. Now, normally, for this kind of spatial data, you'd start thinking about what makes one shape different from another. A long, skinny field versus a more rounded one, right? So, we start from this function here, extract geometry features. This function uses the geometry of each field and pulls out characteristics. Things like how big is the area? What's the perimeter? How compact is it? How close to a circle? It also calculates something called solidity, basically, how much the field fills up the space if you stretched a rubber band around it. Plus, aspect ratio, and even some fancier math things called moment invariance that describe the shape's form. It's designed to handle fields that might even be made of multiple separate polygons. We run this on both our training and test sets to get our first batch of features. Then we just separate out our features from our target, the actual crop type. Okay, now for the really interesting part. Can we get an AI, Gemini in this case, to dream up more features? Maybe some clever ones we didn't think of. First, gotta handle the practicalities. We load our Gemini API key securely. And this little bit of code here, the Gemini rate limiter, is pretty important. It just makes sure we don't hammer the API too fast and hit rate limits. We'll keep it to about 10 requests a minute. Now, we need to tell Gemini what we want. We start by giving it an example of the kind of code we're looking for, which is basically the manual feature function we just saw, extract geometry features. This gives the AI some context like, hey, we're working with geographic shapes and making features like this. Then, we create the generate function. This is the part that actually talks to the Gemini API. And check out the instructions we give it. We're pretty specific. Generate a Python function for feature engineering, use these libraries, look at the example I gave you, but make sure you generate new features that weren't in the example, call your function add new features, make it return a pandas data frame, and give me the code in JSON format. We pass our example code along with this prompt. Alright, now we build the main engine for this experiment, the feature selection function. This is where the automated part really takes off. So, the way this function works is pretty neat. It starts by training our random forest model using only our initial, manually created features. This gives us a baseline score. We're using the F1 score to measure performance. Then it kicks off a loop. In each round of the loop, it does this. It calls Gemini, using our prompt and the best feature generating code it's found so far, starting with just our manual one. It asks Gemini to come up with another function, add new features, with potentially even more new ideas. It takes the code Gemini sends back, assuming it's valid. And then it executes that code Gemini wrote. This creates the new feature calculation function right there on the fly. It uses that brand new function to calculate these newly suggested features for all our data. It then combines these new features with the best set of features it currently has. Next, it retrains the random forest model using this expanded set of features and sees what the F1 score is now. Here's the decider. Did the score go up by a meaningful amount? We set a threshold, say 0.2, so we're not just chasing tiny random fluctuations. If the score did jump up significantly, awesome. We keep this larger set of features as our new best. We also save the code Gemini generated because it was successful, and we'll show it back to Gemini in the next round, hoping it can build on that success. If the score didn't improve enough, or if the generated code had errors, we just toss those new features and let the loop try again with a different idea from Gemini next time. We also have this helper function, train and predict. Its job is just to handle the model training details. It uses stratified cross-validation, which is good practice, calculates the F1 scores, makes predictions on the test data by averaging results from the different validation folds, and puts it all together in a submission file. It tells us the average F1 score it achieved. Okay, moment of truth. Let's actually run this feature selection loop. We'll let it try up to 10 times to find better features using our random forest model. All right, look here. So our baseline score, just with the features created manually, is about 0.586 F1. Okay, decent start. Iteration 1, Gemini generates its first function. Looks like it adds things like eccentricity, rectangularity, stuff like that. We run it, combine the features, train the model, score comes out around 0.6. It's a little better, maybe, but not enough to meet our improvement threshold of 0.2. So the system says, nah, not good enough, and discards these for now. Iteration 2, Gemini tries again, generates another function. This one calculates convexity, elongation, normalized length. We run this code, add these features to our original set, retrain the model. Wow, look at those F1 scores from the cross-validation folds. 0.86, 0.88, 0.86. The average F1 score jumps all the way up to 0.876. That is a huge leap from our 0.586 baseline. Because it smashed our improvement threshold, the system keeps these features, saves this generated code as a success story, and gets ready for the next round. Iteration 3, Gemini sends something back, but oops, looks like the code wasn't quite right or maybe not valid JSON. Invalid function string. Okay, it happens. LLMs aren't perfect. Iterations 4 through 8. Gemini keeps plugging away, generating more functions. But it seems none of the new features it suggests in these rounds manage to push the score significantly higher than the 0.876 we already hit. Sometimes the generated code fails when we try to run it. Iteration 9 and 10. A couple more tries. It generates features like number of sides, form factor, squareness, but again, running the model with these additions doesn't beat our current best score or the code execution fails. So, after 10 attempts, the loop finishes. The best performance we achieved was that fantastic 0.876 F1 score, thanks to the features Gemini came up in iteration 2. We then take the predictions made using that best set of features, our manual ones plus the successful Gemini ones, and save them to our submission data file. And just to see what worked, we can print out the actual Python code that led to the win. It's our original function, plus that second function Gemini generated, the one that added convexity and elongation. That combination was the key. When submitted to the leaderboard, it scores 0.83 and lands me in top 20. So, what does all this mean? Well, it shows that while our human intuition for feature engineering is still super important, these AI tools like Gemini can be incredibly powerful collaborators. It literally wrote code for new features we hadn't initially thought about, and those features dramatically improved our model's accuracy, taking the F1 score from okay-ish territory right up to potentially competition-winning levels. Now, it wasn't flawless, right? Some of its suggestions didn't work or had errors. That's realistic. But the potential here to speed up our workflow and discover effective features we might have missed, that's huge. I'm definitely planning to experiment more with this kind of approach. What do you think? Have you tried anything like this, using LLMs to help with coding or feature engineering? I'd love to hear about it. Drop a comment below. If you enjoyed this or learned something new, hitting that like really helps me out. And of course, if you want to see more experiments and walkthroughs in data science and AI, make sure you're subscribed. Thanks so much for hanging out today. Keep exploring, keep building cool stuff, and I'll catch you in the next video.